Hi, in this video we are going to talk about the area of some standard polygons. In the past lessons we've already talked about what a polygon is and what it isn't. You can see some examples on the screen here. We've talked about the different types of polygons, how many sides they have, what their names are, what a diagonal consists of, a segment going from one vertex to a non-consecutive vertex, and how that affects the formula for the interior angles of a polygon. Because if you divide up a polygon into multiple triangles, you can derive the formula 180 times n minus 2, where n is the number of sides of the polygon. And we also talked about the formula that the exterior angles of a polygon always have a sum of 360. So in a regular polygon, you can just take 360, divide it up into the number of sides, and that'll give you the measure of each exterior angle. And then you could actually recognize that they are supplementary to the interior angles, so just 180 minus that gives you the interior angles of a regular polygon. Regular polygons are the ones that have all the same sides and angles throughout the whole figure. One thing I always like to note when I'm getting into a new topic in geometry is, what is this good for? Think about design, architecture, and basically the world around us can be designed with a lot of polygons, rectangles, squares, triangles, everything. Even in digital form, like in your video games, when they try to render a 3D looking world in front of you, what the computer program is doing behind the scenes to create these objects and characters. A lot of times you can see it better when it's the blocky versions, the ones that are less high quality graphics, but they're basically just making the surface of each object composed of a bunch of polygons. So you can see squares and rectangles and triangles and quadrilaterals of all different shapes, rhombuses and parallelograms. And that makes up, you put them all together on the surface and stitch them together and it makes it look like an object. So computer programs use this all the time. So a few basic words that we will be using repeatedly when we use the area of polygon formulas that we should define. The first one is the word base. Base comes into so many of these formulas, and we're going to define the base as any side of a figure that is temporarily, doesn't have to be temporary, it could be forever, but so we won't even put temporary. We'll say that it's designated as the bottom. And I'm putting that in quotes because it's kind of a relative term, depending on how the polygon is oriented on the page. But here's a little more technical information about that. How does it become the bottom of the figure? Where did my typing go? Hold on. Okay, so more detail on this. The bottom is really a segment from which a perpendicular segment measures the height of the figure. That perpendicular segment would be called the altitude. Remember that from triangles? So whichever side you choose as the bottom, an altitude would be a segment perpendicular to that side that goes across the figure to the highest point on the other side and measures its height. Okay, so that's what we mean by base. The altitude is, I'm going to type this one too. Let me move this. Maybe I'll just try pause it. Okay, bear with me as I'm trying a new technology setup here today. But the altitude is a segment from one vertex of a polygon that is perpendicular to the base. So you see the base and the altitude go together. They mention each other in their definitions. The height of a polygon is basically the length of that altitude segment. How far is it from the base to perpendicular along a perpendicular segment up to the highest point opposite of that base. That's the height, that's the altitude. They're almost go hand in hand. The height is the length of that altitude segment. All right, so I said that we were going to use area formulas to find the areas of polygons, some very common polygons. And we're going to start by looking at the area formula for parallelogram. A parallelogram, we studied, has a base and a height. And you can see in this diagram that the base is one of the parallel sides and the height goes perpendicular between parallel sides. And they've shown this in two different ways, so that if you were to switch it, you'll notice on the first diagram, the top and bottom sides have one little arrow marking each, and these diagonal sides have two markings each. But then the second diagram, they switched it, so they kind of like rotated it. But either way, so depending on which way it's oriented or what you choose to be the base, the height could be different. But it's got to be a perpendicular segment from that base up to the other parallel side so that it represents the height. So with that designation, the formula for a parallelogram area is just base times height. Now, since squares and rectangles are both just specific kinds of parallelograms, they have very similar formulas. The square, we say the base and the height are equal, so if you just call them S, and you put S times S, you get S squared. So the area of a square is just S squared. The area of a rectangle is the same as base times height. Instead of calling it length times width like we did in, say, elementary and middle school, now that we're in geometry in high school, we're going to call it base times height because we recognize that a rectangle is a parallelogram. And parallelogram general formula is base times height. Now, why is that? Because you could really take this, let me make it make, you could take this triangle here and you could move it over. Yeah, there we go. We could take that triangle. Now I didn't want to rotate it, but I want to move it over to here. And if you took it away from this side and put it over on that side, you would end up with a rectangle that is the same base and height as that parallelogram. So the two formulas are the same. All right, we also have talked before about the area of a triangle. I'm pretty sure that you've been doing that since middle school, but the area of a triangle is just 1/2 base times height. Once again, the base could be any of the sides, but the height would have to be a perpendicular segment from that side you chose as the base, going across the triangle to the opposite vertex. And then your formula is 1/2 base times height. For the area of a trapezoid, it's 1/2 the height, which is again a perpendicular segment between the bases, but this time the two bases are different lengths. That's the definition of trapezoid. We already talked about that in the quadrilaterals unit. But the average of the bases, basically 1/2 B1 plus B2, that's the average of the bases, times the height gives you the area of the trapezoid. Sometimes it's written like this, 1/2 times the height times the sum of the bases. You could put sum of the bases over 2 times h and it would be the same thing, okay? But that's the formula for area of a trapezoid. Area of a rhombus. The easiest way to find the area of a rhombus is if you know the length of each diagonal. Okay, the diagonals are going from vertex to opposite vertex. These two segments down the center of the figure are the diagonals, and then the area is just 1/2 the product of the diagonals, D1 times D2. So that's a pretty simple formula, but you had to know the length of each diagonal. Okay, and we talked last time about the area of a sector being a portion of the circle, so it corresponds to the same portion as the arc here, which is a angle measure, out of 360, times the circumference of the circle. I'm sorry, the area of the circle. All right, our first example, we're going to find the area of a parallelogram. I think today we're going to skip perimeter. Perimeter would be pretty simple for this. It would be 12 plus 18 plus 12 plus 18. So you could figure that out, just adding up the sides. We've been given the sides. But what makes this a high school geometry problem is finding the area of this parallelogram is not quite as straightforward because we haven't just been given the two parts that we need, base and height. You know, the area formula is area equals base times height. If we had been given the base, well, we could call this the base, right? This would be the same amount, 18, so we could designate that as the base. But then we need to know what is this, because that's really the height. 12 inches is not the height. This is not the height. The perpendicular segment is the height. So I'm going to, let's see, erase the little question mark, and I'm going to label it with H for height. So I'm going to say 18 is going to go into the formula for base, but I still have to fill in that height in order to figure out the area. In this case, the way I'm going to do that is to recognize that that segment is part of a little right triangle. So I am going to find H. Whoa. Let me stop a minute. So I just duplicated that little triangle, and I'm looking at it as, okay, that's a 60-degree angle, this is a 90-degree angle, this has to be 30, so it's a special right triangle, 30, 60, 90. We learned about that in a previous chapter, that special right triangles have special relationships between the legs as well. So the hypotenuse is 12, and I can tell H is the long leg because it is across from the bigger angle, 60. 30 is the short leg. If you recall, in a 30, 60, 90 triangle, the short leg is always half the hypotenuse. So I can fill in this would be 6. And then the long leg is always the short leg times radical 3. So that tells me H is 6 radical 3. Now I know the height of my parallelogram, 6 radical 3. And now I can fill that in to the area formula. The height is 6 radical 3. And we're just going to simplify that by doing 18 times 6 radical 3. And I might just kind of leave it 18 times 6. I'll leave it in radical form. It's 108 times radical 3. And that's the most exact answer of this, and it's inches squared because it's an area. If you want an approximate answer, you're just going to put that into decimal form. Your calculator can do that for you. And you should get 187.1. And that would be square inches. Okay. Okay, for this next second example, the coordinates have already been plotted of this quadrilateral, and we are just supposed to determine what shape it is and find its area. Clearly, I think we all could agree it is not a square. It is not a rectangle. It's a parallelogram. Either way, it is going to be base times height. So we just need to find the base and the height and multiply them because we know the area of a parallelogram is base times height. In this case, I'm going to designate DC as the base. To me, it just makes sense that the bottom side would be the base. And I can count on the coordinate plane. It's 4 units on this side and 2 units on this side. It's a total of 6 units, so B equals 6. The height has to be a line perpendicular to the base, not one of these diagonals. That is not the height. The height would be one of these vertical perpendicular lines, and those have a length of 3 units. So the height in this case is 3. Therefore, the area of this parallelogram is 6 times 3, which is 18 units squared. All right. Example 3 doesn't seem to be any of the polygons that I had given us formulas for at the beginning. It is a quadrilateral, but it's not a parallelogram, it's not a trapezoid, it's not a rhombus. So sometimes we are going to try to look at a figure as a composite of other recognizable figures. And in this case, we're going to see this or look at this as if it were two triangles. And that's exactly what it says in the note here. The area of this quadrilateral is the sum of triangle XWZ, the bottom triangle, and XYZ, the top triangle. So it says find the area of the quadrilateral if you know that XZ is 39, HW is 20, and YG is 21. So I'm going to write here that the area of this figure is equal to the sum of triangle XWZ, that's the bottom one, plus triangle XYZ. And I'm going to use the formula for triangle area for each of them. 1/2 base times height. Now, what is the base of triangle XWZ? If we try to say this, that's not going to make sense. If we try to say that, it's not going to make sense because we aren't being shown a perpendicular segment going from either of those sides across the triangle. The one side we do have that has a perpendicular segment meeting it is XZ. So XZ is going to be considered the base, and that value is 39. And then the height will be, whoops, I got to get rid of that one marking there. Okay, it's just 39. The height is HW, that's 20. So 1/2 of 39 times 20 is 390. I just decided to do half of 20 in my head is 10 times 3. Okay, this is probably like the third time I've had to change my surroundings because I had a dog bothering me or kid making noise. Now there was lawn equipment going off right outside the window. Here we are, back again. All right, so that was the first triangle. The second triangle is the upper one, and that's a lot easier to see why XZ is the base because it is the bottom of the upper triangle. XZ is still 39, so that's the base, and the height is YG, which is told to us to be 21. So 1/2 39 times 21 is going to be 409.5. Okay, put it in there, and the total for the area is approximately it's actually exactly 799.5 square units. And that is your answer for number 3. All right, this problem gives us a rhombus ABCD, and we are told that the area is 100 square meters. This is a high school geometry problem where we aren't just given the two parts of the formula to plug in and calculate. We're going to have to think of it a little bit differently. We've been given the area, and we're supposed to figure out one of the diagonals. So I'm going to place the 100 in for area. And then the diagonal that they gave us, AC, that's one of the diagonals, is 10. So the question is, what's the other diagonal? And I cannot seem to write neatly on this. I'm going to start that. I got to have a 10 there. 10 times D2. Okay. So we need to solve for D2 because D2 is BD. BD is the other diagonal, D2. Okay. So let's just simplify this. Half of 10 is 5. And so 100 equals 5 times the second diagonal. Therefore, the second diagonal equals 20 meters. So that was just a little bit of a backwards type of question. Instead of them giving us the two diagonals and asking for the area using the formula, we had to do the opposite. And question 5 is very similar to that. We've been given a trapezoid where they told us that B1 is 20 and B2 is 30, and the area is 250 square inches. So find the height, AE. I'm just going to put H on that segment, AE. So let's write down the formula for the area of a trapezoid, it's 1/2 the height times the sum of the two bases. Okay, so 1/2 h times 20 plus 30. All right, let me simplify a little bit. We have 1/2 h times 50, or 25h is how that looks on one side. And we're told the area is 250 square inches, so I can put that over here where A in the formula is. So to find the height, we just have to isolate h, which is simply dividing both sides by 25, and therefore h ends up equaling 10. So the height of this trapezoid is 10 inches. All right, this is a hexagon. It says it is a regular hexagon that has a side length of 8, and we're supposed to use just that to find the area of the entire figure. So I'm just going to write an 8 on one of the sides. Maybe I'll even put an 8 down here to represent that side. And what we're going to do is think of this hexagon, since it's not one of the figures that we have a formula for, we're going to think of it as, oh, and it's regular, which means that every angle and every side, every angle is equal and every side is equal. So if we draw this one triangle coming out from the center, using these like radii type segments, all of the other ones will be equal. So we can figure out this measure of each interior angle because it's a regular hexagon, because the exterior angle, there are 6 of them. 360 divided by 6 is 60. So that means the interior angle that it is a linear pair with would have to be 120. That means this triangle here, if that's 120, then this right here is 60. And that means that this is also 60. And this is 60. And if you split it down the middle in half, that's a 30. So we basically have this AGF triangle is a pair of 30, 60, 90 triangles back to back. All right, what would be the bottom or base of that 30, 60, 90 triangle? It would be half of this part, which would be 4. So I can actually figure out the height of this triangle, since it's 30, 60, 90, just because 4 is the short leg across from the 30-degree angle. I can find the long leg over here by doing short leg times radical 3. So that would be 4 radical 3. So for this triangle, the area of it is 1/2 base times height, and that would be 1/2 the base. Now the base of the entire triangle now I'm talking about is 8, and the height is 4 radical 3. That's a mess. I gotta make that a little neater. So this is going to be, now I'm looking at this whole triangle, this AGF is 1/2 8 times 4 radical 3. Oh, I hate the way my handwriting looks on these whiteboard apps. I have got to get this worked out. Or I guess I'll just go back to writing on the wall. Anyway, so half of 8 is 4. 4 times 4 is 16. 16 radical 3 is the area of one of these triangles. Now this hexagon is made up of how many of those triangles? 6, right. So the hexagon area equals 6 times 16 radical 3. Now I am going to need a calculator to help me with that. It's 96 radical, which comes out to 166.3. It's really 0.27. I'm rounding it to 0.3. But that would be in whatever unit measure this 8 was. They didn't really say. They just said 8. So we'll call it units squared again. Okay. 166.3 is the final answer. Okay, number 7. Find the area of the shaded region, given that the triangle is equilateral. Once again, familiar shapes, but the shaded region is not exactly a circle. It's part of a circle. It's not an arc either. I mean a sector, because it's not coming out from the center of the circle, making an angle. But what we would do is, if this was the whole circle, of course, we have a formula for that. Area is pi r squared, right, for the circle. So what's the radius of the circle? 2.4 centimeters. We could at least find that much. Pi times 2.4 squared. And I'm going to go to a calculator. 2.4 squared is 5.76. So that's just the area of the circle itself. But the shaded region has like the triangle part kind of cut out of it. So it's the circle minus the triangle, area of the triangle. Now we know that the area of a triangle is 1/2 its base times its height. So I'm just going to write that formula there. But on this triangle, we have not been given either of those values, base or height. We've been given some other segment kind of going from what looks like a center of this triangle out to a vertex, 2.4, which is the same thing as the radius of the circle. Now, since this triangle is equilateral and it is inscribed in the triangle, that kind of segment going from the center on out is kind of like a standard thing to see for a polygon like this inscribed in a circle. But we're going to have to break this down into figuring out how to get the area of this white triangle from just that 2.4. So I'm going to drop a little segment down here that would be perpendicular to the bottom of that triangle. And then I'm going to recognize that since it's equilateral, all of the angles are 60, including this one. And when I cut it in half with this segment going like that, it's all symmetrical, right? That's 30. So this is now a 30, 60, 90 triangle with 2.4 as the hypotenuse. I can now find this segment and this segment because it's a 30, 60, 90 triangle. So starting from the hypotenuse, the easiest thing to find is the short leg. It's half of the hypotenuse. That would be 1.2. So this little segment here is 1.2. The bottom part is the long leg of the 30, 60, 90 triangle, and that's going to be 1.2 times radical 3. Now I'm going to go off on my calculator and do that, and I'm going to give you a chance to do it while I go. I have got only my phone calculator with me right now. It's going to take me a little extra time, but I'm going to do square root of 3 times 1.2. I don't like the phone calculator personally, but I know how to use it. So I got 2.1 or 2.078. I'm going to round it to 2.1. So that is the bottom of that little triangle, 2.1. Now, when we're talking about the full triangle, we need the base of that, which looks to be twice what we just found. 2.1 times 2 is 4.2. Okay, so now we have the base of our white triangle. The height of our white triangle starts with this little segment, but it's also got another whole portion to it. How am I going to get that measure? Hey, wait a minute, that's just another one of these. It's the same as the radius of the circle. So that part up there is 2.4 plus this part, which is 1.2. So the height of this triangle is 3.6. Now I've got the stuff I need to plug into this formula up here for the white triangle base and height. 1/2 the base of 4.2 times the height of 3.6. Okay, let's go and calculate that. 4.2 times 3.6 divided by 2, or times 1/2. I get 7.56. Now I'm going to, let's see, give my final answer right here, because I still need to put together two things. There's the circle minus the triangle to get the shaded region, right? If you cut out the triangle from the circle, you get the shaded region. So 5.76 pi, well, 5.76 times pi minus, that's 18.09, minus 7.56, I'm getting 10.5. And that would be centimeters squared, because this is an area. So there's a couple things going on in this problem, quite a few. We had to recognize the shaded region as a circle minus a triangle, and we know the two different formulas for circle and triangle, but we then had to calculate the base and height of the big triangle by breaking it into an even smaller triangle and using 30, 60, 90s. So it's pretty complex. All right, our last example today, number 8. Now we are finding the area of a shaded region where the triangle is the big shape and the circle is being cut out from it, because we just want the shaded region. So the model for this is basically triangle. When am I going to learn? I got to turn it back to, there we go. It's triangle area minus circle area is what our model is going to be. So the area of a triangle is 1/2 base times height, and then the circle area is pi r squared. So there's our two equations we're going to use and fill in. But we may have to go off to the side and find some of these other values once again. Do we know the radius of the circle? I think that pops out to me as being the most obvious thing in this diagram, that the radius of the circle is 3 inches. So I'm just going to start by plugging that right in there. I like to just kind of get something started. Okay, now ultimately you have to figure out the base of the triangle and the height of the triangle, and then I can just do this calculation and I have my answer. So let me think about this triangle. This 3 inches, once again, I'm going to break it into a smaller triangle like that has 3 inches as the height, and since this is an equilateral triangle, all of these are 60, and that means this in here is 30, this is 90, and this is 60. So I have once again another 30, 60, 90 triangle where the short leg is 3. The long leg is going to be 3 times radical 3. The hypotenuse would be good to know as well because, well, we're going to need that to complete the big triangle's height, okay? So the hypotenuse is always the short leg times 2. So this line is 6 inches, okay? But this line, since there's a lot of symmetry going on here, is the same as this line from the center of that figure out to a vertex. So if we basically kind of tilt our heads a little bit this way, and we think of the base of the triangle being this length, and this would be the height, okay? So that's the height, and this is the base. All right, so we're talking these base and height. The whole big main triangle base, I can tell, is 2 of these pieces? 3 radical 3. So what's 2 times 3 radical 3? That would be 6 radical 3. And the height we just found was this little segment plus the 6, so that's 9. Oh my gosh, I've got all the parts plugged in. I just have to calculate. So I'm going to go back to blue. Half of 6 radical 3 times 9, so that would be 3 radical 3 times 9. That's 27 radical 3 minus 9 pi. Well, this is the most accurate, exact answer in inches squared because it's irrational in 2 ways. There's a radical and there's a pi. But that doesn't give me a very good feel for how many square inches it is, so I'm going to actually go ahead and do the calculations of 27 times radical 3. And on my iPhone calculator, I have to first put in the 3, take the square root, and then multiply by 27. That part comes out to be 46.7 or 8 if I round it. And then I have to do 9 times pi. That is 28.27. I'll say 28.3. So the approximate answer, 46.8, that's the triangle area, minus the circle area of 28.3 is going to be approximately 18.5 square inches. So this is a shaded region that's a composite of 2 figures. We're starting with the outer one and subtracting away the inner one. And once again, we used a lot of 30, 60, 90 triangle ideas here just to do some problem solving and figure out the parts that we needed to plug into the formula. So that's it for today, and I'll see you next time.